All right, so let's begin our Math Dog review. I'm reviewing this worksheet that goes over all the skills that we need for our test. And in any case, what you probably should do is, if you haven't already, take the blank version and do your best to answer these questions, and then turn me back on to review with you. I'm taking the key that's posted for your viewing pleasures, and I'm basically talking you through these problems. So let's get started with the first skill. The first skill is to determine the formula mass of a compound. This compound has a particular chemical formulas, as all formulas do. Okay, so party people, we look at this magnesium phosphate. If we look carefully in one of these formulas, okay, it's the one way to do this. In one of these formulas, we have 3 magnesiums. And if you look at the parentheses of the phosphate ion, we have 2 of everything inside. Since there's 1 phosphorus or 1 P, that means there's 2 P's or 2 phosphorus atoms. And then, of course, you can say, well, there's 4 oxygens already in here, but if there's 2 of them, 2 times 4 is 8. And all I'm doing to get the formula mass, this is a ionic compound, so we talk about the formula. If it was a molecular compound with nonmetals and nonmetals, okay, we would say molecular mass, but it really means the same thing. What we're going to do is we're going to take all the atoms and their ratios, in this case 3 magnesiums, we're going to times it by the atomic mass, and we get a certain value. And we have 2 phosphorus atoms, and we times that by 31, its atomic mass. We should know where to get that from our periodic table. And we get a total mass of 62 grams for all the 2 phosphorus atoms. And we do the same thing for the 8 oxygen atoms. We times each atomic mass of oxygen by 8 and get a total mass there. And all we're doing is going to add up all the atoms, their collective atomic masses, to get an overall gram formula mass, or if this is a molecular compound, a molecular mass. It means the same thing, but very carefully, it's grams per mole. So if you were going to convert some amount of, let's say, grams of magnesium phosphate into moles, or convert some moles of magnesium phosphate into grams, my friend, you would be using this value as your converting factor. But that's all you're doing, is adding up all the atoms based upon how many they are in a single formula, using the atomic mass given to you in your periodic table, and collectively coming up with what we call a formula mass. And they're very simple. It's the mass of 1 mole. And sometimes they love to ask you, hey, if I have 1 mole of magnesium phosphate, how many grams would that be? Well, of course, it would be 262. Okay, another skill that is very much related to number 1 is the skill of taking the percent by mass of a certain compound. So in this question, I made it very easy. I said, what's the percent by mass of phosphorus in this same formula? Notice the formula number 1 is the same as the formula in number 2. So this formula here is the same here. Okay, so how do we do a percent by mass? As I always say to my students, a percent by mass is always a part over total, in this case the whole, times 100. Well, what are we going to use for the total? We're going to use the mass of 1 mole. If we know no information, we know the percent by mass of compounds stay constant because, well, their formulas stay constant. So if their formulas stay constant, their percent by mass of each of the elements that make the formula stay constant. So the short story of it all is we're going to find the mass of 1 mole. So sometimes they give you this, and we're going to see that in other questions. But we had to actually calculate it. And that's going to be my total. That's going to be the mass of 1 mole there. And what part are they asking for? Well, when we do a percent by mass of water and a hydrate, the water was my part, but they're asking specifically about the phosphorus. Okay, so if I look at my work above, I can clearly see that we found that the mass of the phosphorus, there's 2 phosphorus atoms in that formula. So 2 times atomic mass is 62. So 62 grams out of 262 is what we set up here. So out of the total mass, if we had 1 mole, but it wouldn't matter because, again, the percentages stay constant, 62 grams of it, based upon my work above in the formula mass, is due to the phosphorus. In any case, that's my part, divided by my total times 100, and we get our 23.7%. This is a percent by mass. 1 and 2 are all about using the mass per 1 mole, in this case the percent by mass. Okay, now number 3 says how many moles of oxygen are in 4 moles of this hydrate formula. Okay, so this hydrate formula is something that we're using in our hydrate labs, and very simple, that dot right there just means with 5 water. So a hydrate is a salt, an ionic compound, metal and nonmetal, in this case a metal and a polyatomic ion. And it's a salt, it's a crystal, and it has 5 water molecules locked in that ratio, in that crystal. So the way to answer a question like this, it's a ratio question, I say, okay, they want how many moles of oxygen atoms, I really should say, are in 4 moles of this. Okay, so how many moles of oxygen atoms? All right, well, I always say to my students, how many O's or oxygens are in 1 of these right here? And that's what I did right here in my work. I said, okay, there are 4 oxygens from the sulfate, and I got 5 from the water. Notice there's a 5 in front. That's why I have this drawn here. And there's 5 oxygens for a total of 9 oxygen atoms are in 1 of these formulas. Now, if I have a mole of this formula, there's 9 times as much. So if I have 1 mole of it, there's 9 times. But they didn't ask for 1 mole. They asked for 4. So it's kind of a ratio question if you want to think of it that way. And if you want to, you can do a proportion. I said, okay, in 1 of them, there's 9. They said, what if I have 4 moles of them? Well, solve for it. Okay, so in 1 there's 9. If it's 4, there's 4 times 9. Notice the 1 to 9 is increasing 9 times, so this will increase 9 times. So you're really timesing by 9. If you don't like the math, this, crisscross or cross multiply, and you find that x is 36. Another way to think about this is this. If there's every 1, there's 9. If there's 4, 4 times 9 is 36. So it's a ratio. It's a 1 to 9 ratio. I asked for 4. So 4 times 9 is 36, and that's all there is to it. No math about that. Really, there is a little bit of math, but it's just a ratio. Every one of those formulas, there's 5. I could do this up here too. If I give you the magnesium phosphate again, I could say in 1 mole of this formula, I know I got stuff going on here, in 1 mole of this formula, how many moles of the phosphorus atom? Well, we just saw that there are 2 of these because of that 2 there. So in 1 mole of this formula, there's 2 moles of phosphorus atoms. Same idea, party people, including Ava. Okay, so in any case, let's get going. All right, so let's continue on this little journey that we're having together, and I hope you're enjoying that. And we're going to scroll down, and we're going to get to this number 4 question, which is a hydrate lab. Given the following experimental data. Experimental data is data that we get from taking the compound, okay, massing it out, heating it, remassing it out, and finding the results. In any case, they want the percent by mass of water. Oh my gosh, percent by mass. That is, again, part over total times 100. Another example, except this time it is based on an experiment that we actually did. So in order to do the percent by mass, and they want water, party people, okay, the water is going to be my part, okay? The total is going to be the total mass of what we call the hydrate. What's the hydrate? The hydrate is a salt with water. The anhydrate, after we heat it, is just going to be the salt. The water is going to leave. So when we find the hydrate, which they just gave it to us, and the anhydrate, we subtract. We have the chemical with the water, the one without the water. The difference is the water. So we have to subtract the mass that's lost that we're after, and that's the water. Okay, and that's where I come up with the mass of the water is 1.21. I just subtracted these 2 numbers. Okay, the anhydrate from the hydrate. And the total is going to be the mass of the salt that I started with, is the salt and the water, and that's what is the mass of the hydrate. Okay, any case, put the mass of the water that you got by subtracting over the total mass that we started with times 100, and you should get 23.7, part over total times 100. That should be straightforward. We've done 2 labs with that. Okay, moving on. Number 5. What is the empirical formula of C8H18? Okay, well, that is easy for you to probably say, but not for me. But it is the lowest ratio. The empirical formula is the lowest ratio. So divide by 2 until you can't anymore, all right? Or maybe you have to take a common factor sometimes. But the easiest thing here is keep simplifying in this until you cannot divide it into a whole number anymore. In this case, we divided by 2. I can't keep going here because half of 9 would, of course, be 4.5, and they want the lowest whole number. So the lowest ratio is C4H9. That's the empirical. By the way, this right here would be called the molecular formula. That's the example of the actual molecule that has the actual atoms bonded in that ratio. So molecular formula versus the empirical. They wanted the empirical, they wanted the lowest ratio. I think that's easy as pie. I say easy as pie is eating pie, maybe, I don't know. Okay, so here comes an older question, but one that is a little bit complicated, but kind of one we've done already in lab. If I give you the percentages of the masses of the elements, okay, can you come up with the chemical formula? In this case, we want the lowest ratio. Well, my friends in chemistry, the chemical formula, in this case, empirical formula, just like any chemical formula, is a ratio of how many. In this case, there were 4 carbons for every 9. This is a how many ratio, not a how heavy. We have to be in moles. So in my problem, I'm going to take my percentages given, just like we got in our labs. We're going to assume a 100-gram sample. So in 100 grams, 31.4% becomes 31.4 grams, right? So we assume a 100-gram sample. You could assume a greater than 100 grams, and then your grams are bigger. If you assumed a 1,000-gram sample, it'd be, okay, 314. So it's your choice. I think 100's easy because the percentage becomes exactly the grams, right? So that's important. We're going to convert the percentage to grams because of a 100-gram sample. That's exactly. Now, grams are not going to help me here. I'm trying to build an empirical formula. I have to be in a mole value. So here comes this gram atomic mass. You can call it a formula mass, but it's the mass per 1 mole. Where am I getting this from? Well, they said we had titanium. So I looked up the atomic mass of titanium. It was 48 grams. I put grams on the bottom because I want the grams to cancel so I can get the moles, the unit left standing. Okay, so I do that for both, except for chlorine, my atomic mass is 35. I know it's 35.4. We're just going to round off. And I'm converting to moles. You must be able to go from grams to moles and moles to gram. Here's an example. Okay, and once I get my moles, this is a how many number. And if you can't see it, divide by the smallest number. If 0.654 is a small number, it's smaller than 1.96, so divide it by itself, you get a ratio of 1. And 1.96 divided by 0.653 is almost 3. You can round off. And what we have is a 3-to-1 ratio. And what does that mean? Well, that means that there's 1 titanium, that's the 1, to 3 chlorines. And my lowest ratio is Ti, there's 1. We don't write the subscript 1 there. Okay, and chlorine 3. All right, so we built the empirical formula where I'm taking the percentages, making them into grams by assuming a 100-gram sample, converting to moles by using their individual atomic masses, and then trying to see the ratio. Sometimes the ratio is easy to see by eyeballing it, okay, or just divide by the smallest number and the ratio will pop out, okay, but we needed to get to moles. Chemical formulas are ratios. In this ratio, there are 3 chlorine atoms to 1 titanium. Okay, let's go on to the next question. And this question states, hey, a chemical with an empirical form of CH2O has a molecular mass of 180. What is its molecular formula? Okay, well, they're giving me the empirical formula, the lowest ratio. So I call it the box question. So I put the lowest ratio right here. Because it's on the bottom, it's the lowest ratio. What did they give me in this problem? Well, they gave me the molecular mass. And they gave me the lowest ratio, empirical. We want to know what the actual formula, that's what the molecular mass is. If you get this question wrong, it's normally because you just don't know what molecular. It's the actual formula of the molecule that can have multiples of the empirical. Okay, any case, I know the question is done for you, but we started with what's in green. So the next thing I do is find the mass of my empirical. I find the formula mass or the molecular mass, and I add them up, and I did that here, and I got 30. And look what I hear. 180 divided by 30 is 6. The molecular mass is 6 times greater. That's why I have the arrow going up here 6 times. And if it's 6 times over here, it's 6 times over here. So carbon times 6 is C6. H2 times 6, hey, 2 times 6 is 12. And this is an O by itself, and that's where I get the formula. Now, you could do this easier because I gave you 180. And if this was a multiple choice question, you could see which choice, and they usually give you formulas, adds up to 180, but this is how you would normally do it. I do this way with my AP kids as well. I call it the box question, but we're just trying to see, which molecular formula, or what is the molecular formula from the empirical, given a couple of things. And what we're given is, of course, the actual mass of the molecular formula, and we're given the actual empirical. Find its mass, and then see how much bigger the molecular is. That's how much bigger the molecular formula is. Okay? All right. So back on our horse here with number 8. And this is, again, a percent by mass hydrate lab. Oh, my God, this is experimental data. So we need to find the hydrate and the anhydrate. Boy, we kind of did one already, did we? And this was simplified. They just gave us this value. So we subtracted, and we got the water. And we put the water over the total hydrate, and we got this value. Well, in this question, not so simple. We need the mass of our hydrate and the mass of our anhydrate. So I notice my hydrate is right here, but that's with the crucible and cover, which is basically my container. This is the mass of my container. So I subtract these two out to get the container's mass, and I've got my hydrate mass. Now down here, you notice we kept heating this compound, and we kept massing it out until we noticed the mass stayed constant, because that told us when the water was driven off. But this is the anhydrate. It's a word for the dried form of this hydrate with water. And notice it has the mass of the crucible and cover. So I'm going to subtract out the what? Subtract out the container in this case, and I get 3.3. That's my dried compound. Just like the other problem, I'm going to subtract these two and get the water. They were asking for the mass of the water for number 1. So I just, hey, that's the hydrate. That's the salt with the water, salt without the water. The missing mass is the water. But you had to work out, this lab data, and this should be easy since we actually did 2 of these hydrate labs. There's a reason for my madness. Okay? Now, number 9, they want the percent by mass of water in this hydrate. So we're just going to take this data. We have, percent by mass, part over total times 100. The part they're asking for is the water, and the whole, of course, is the hydrate. And, of course, you times it by 100, and you get 24.5%. Okay? All right, number 10 was like our copper iodide lab. Experimentally, we figured out how many grams of copper reacted, and experimentally, we figured out how many grams of iodine reacted. But grams are not going to help us because a formula that we're trying to build is based upon a how many ratio. So we need moles. So here we go, converting to moles again. So I need the atomic mass of copper, and I put grams in the bottom so it cancels out, and I got moles. I need the atomic mass of iodine. I'm rounding to whole numbers. I put the grams on the bottom so they cancel, so I'm dividing by that. And you could probably eyeball this. 0.628 is twice as big as 0.34. So that's a 2-to-1 ratio. If you don't see it, divide by the smallest number. Hey, we've seen this problem before, haven't we? Yes, we have. The first one of this page, we took the percentages and we did exactly this. Except in our lab, we don't get percentages, we get the grams. So this is exactly what we just did. Okay, there's a reason for my madness. Okay, all right. So any case, I convert to moles. I see it's a 1-to-2 ratio, and there's 1 copper to 2 iodines. And there's my formula. Notice it's the lowest ratio. It is an empirical formula. Okay, hopefully you're getting this. Number 11. Okay, this is balancing. And the key, I kind of explained how I did this. All right, so I'm going to kind of restart this if you're having problem balancing. So I'm going to kind of white this out. It'll be all white in a second. So I'm just going to take this and just, I know we know the answers, but I'm going to let you see my thinking here. All right, and I'll just make this here. And again, all I'm going to do here is just take this stuff out so you can watch me balance. I'm trying to explain it in the key, but it's kind of confusing. trying to do it without it. Okay, so let's get a color here. So here's my first thing. I got one sodium. I've got two N's. Ooh, I have one N here. So I can see that that's a problem. So I'm going to put a 2 here. That's going to balance my nitrogens, right? All right. Now hold on. This gives me 2 nitrogens here. So I have to put a 2 here. And you can see right now that our nitrogens and our sodiums are balanced on both sides. But notice something, and again, it's kind of confusing if I add too many things here, but if I was to give you a different color, it'll make more sense. This 2 means I have 2 nitrate ions. Each nitrate has an N. We've got that covered with the nitrogen because we need 2 N's on this side, and because, hey, N2 is a Hofprinkel, it bonds to itself, it's diatomic, we can just leave a 1 here, okay? And hopefully there was a 1 there before, and that gives you 2, and that's the easy answer there, but we got to balance the O's. And of course, because there's 2 of these NO3s right here, that means there's 6 oxygens. To get 6, I need 3. Okay, and so that's my thinking behind that. Do I have a 2 there? Yeah, that's not good. Okay, that is a problem with my key, and I feel bad, but now I'm over it. Okay, so that should be a 1, not a 2. All right, and you guys found another mistake. Good for you. Or I found it. Okay, good for me. So let's get that off. Okay, so if you're saying, Mr. Krotsky, I understand that. Well, it's because I had the wrong number. That should be a 1 there. Because it's N2, I just need a 1. All right, so I'll put that there. And I hope you guys get it in spite of me. Okay, good. All right. Any case, the answer would be a 1. All right, so what's the name of the reverse reaction? Well, if I wrote the reverse reaction, okay, is that one thing is breaking apart into 3 things. That's decomposition. All right, if we go the reverse, because we should know that synthesis is the what? Reverse of decomposition. Okay, so that's why number 2 in the forward, it's decomposition. If I ask for the reverse, you're making something. That'd be synthesis. That's pretty straightforward. All right, number 3. What is the coefficient in front of the oxygen in the correctly completed and balanced reaction? Okay, so again, because I have the answers here, it's kind of confusing. I know I did this one right, hopefully anyway. So let me just kind of white this out. Again, it'll be all white. Okay. And again, if you're not used to these bad jokes, then you need to turn my video off. Okay, now, so let's put this back on and put to a color we can see. Now, I know that this is going to be decomposition. It's going to decompose into its elements. So it's going to decompose to magnesium. Magnesium is not a Hofprinkel. Hofprinkels are diatomic elements. I use this mnemonic Hofprinkel to remind myself that if I have that element, it has to be bonded to itself. I have an O here. Because it's a Hofprinkel, I have to write O2. I have an H here. Because it's a Hofprinkel, I have to write H2. Now I'm going to try to balance. 1 magnesium here, 1 magnesium. Oh, little 2 here means I have 2 O's. Oh, I already have that with an O2. Okay, I have 2 H2s. Because I have H2 here, it's already balanced. So what's the coefficient in front of the oxygen? Hey, there's nothing in front, it implies 1. Right? Nothing in front implies 1. If I have 1 apple, okay, I don't have to say 1 apple, it's just an apple. Okay, so in any case, that's how that works. But the tricky part is understanding that it's going to break down into its elements. Some elements are diatomic, so you have to make them into that based upon that mnemonic. What's the name of the chemical reaction in reverse? So I wrote it in reverse. And if things come together, okay, if they come together into 1, then you're making something. It's synthesis, right? Okay, we can do this. Number 5. All right, so this one, again, same idea. I was trying to explain how this works, so I'm going to white this out. Yeah, you know I'm going to go there. It'll be all, yep, we won't say it. But I'm just going to get rid of these numbers and explain them. Okay, let's pick a color we can see. All right, so again, it's a puzzle. We can start this many ways. So I said I started with number 1 here. I noticed there was 2 of these phosphates. I'm going to keep the PO4s together. Okay, and I noticed there is only 1 phosphate over here, so I put a 2 here. because that will give me 2 phosphates. I'm going to keep the PO4s together. It's easier if you do that. However, follow the red arrow here. Now it's the black arrow. That's going to give me 2 times 3, 6 potassiums or Ks. There's 1 K over here, so I throw a 6 here. That, if you follow this line, I don't know what color, there's 6 nitrates. Notice there's 2 nitrates on this side. Remember, I'm keeping the NO3 together. What times 2 is going to give me the 6 nitrates, because there's 6 nitrates here. Hey, you got it. I need a 3. And that's going to give me 3 calciums, and lo and behold, we already have that. So that's it balanced. Okay, and I tried to kind of explain that, but you certainly could do it many ways. But the whole thing I'm trying to show you is that the same number of atoms and types are on both sides. That's called law of conservation of mass. Okay, all right, on the home stretch here, last page, number 6. Okay, now this is a question where they give you a balanced chemical reaction and they give you moles. And all you're going to do is make a proportion. It's the easiest way to do this. In our course, it's a mole to mole always. For those that are checking in from different places, yeah, there's probably a better way to do this, but this is the easiest way to get my students through this part of the math. So they gave me 3.5 moles of aluminum. So I put the 3.5 above the aluminum. They want to know how much copper will be produced. That's why I put the X over. And this is the part that is the whole part of this. The mole ratio, the coefficient, becomes the denominator. So the 2 goes in the bottom here. So when you think about it, I got 13 over 2, 13.5 over 2 is equal to X over 3. Do that proportion, cross multiply, you'll get 20.3. For those that really can see what's happening here, the ratio is 2 to 3. Okay, so the ratio is 2 to 3. So what does that mean? Well, that means that if I'm going to go from 13.5 and 2 to 3, you should recognize that 3 is 1.5 times bigger than 2. So you're really timesing this by 1.5 times. And that gives you the same answer. You don't have to think that way. You can just, plug this in. But again, put the number they give you in moles over the chemical that they're talking about. They gave me 13.5 moles of aluminum. The coefficient in front is the denominator. Make that go below. Put the X over the one they're asking about. Who cares about the rest? They have to be there. They're going to be there, but we're not really involved with them in solving this problem. We don't need their information. So the X goes over the copper, the 3 goes in the bottom, and we have the same proportion solved for it. It's just that easy, party people. Okay, and Eva. Number 7. Now, this, my friend, is the more balancing. So let's go through and make this go white. Okay, and again, no more Bob Marley type of references. Okay, even though I know the movie's out. All right. And by the time people watch this, the movie will be too old. Okay, but in any case, I'm going to start this way. So let's again pick a little, I'll go with red here. So I'm going to go with 1 iron, 1 copper, 1 copper. We're so good, but now the problem is I've got 2 chlorines and I got 3 chlorines. I need a common factor. The least common factor between 3 and 2 is 6. To get 6 chlorines over here, I throw a 3. Or I write a 3. Hard to throw a 3. All right? 3s are heavy. Now, 3 times 2 by the distributive property is 6. Hold on. We want 6 over here, so we're going to put a 2 here because 2 times 3 is 6. But we've kind of disrupted our balancing here. We have 3 coppers now. So we've got to put 3 here. And now we've got what? 2 irons. We put that there. And that's how we balance that. Right? Okay, so number 8 says, what's the name of the chemical reaction, number 7? Okay, well, you notice the iron is replacing the copper. It's got nothing, there's not 2 things replacing. That's why we call it single replacement, right? In the reaction down here, we have 2 chemicals that are switching places, and that's double replacement. This is single because this one's by itself already, and it's switching out the calcium. It's a redox reaction, but you should be able to identify that as a single replacement. There's no reverse to it, by the way. In the reverse, it's also single replacement. But number 9, I'm asking you to predict any one of the 2 products. And you've got to understand that in this reaction, the positive metal ion is in front in both cases, always. The negative ion is behind, I should say, the positive ions, okay? And when you double replacement, this positive of this chemical, remember this is 1 salt, It's got a positive side and negative. This positive is going to hook up with this negative, make lead sulfate. And the charges are not necessary. I'm just trying to teach you that. And the potassium nitrate, goes over here. Okay? Notice I'm still leading with the element, or in this case, the ion, that's positive. That's the IUPAC naming system. All right? And we're just switching partners, and we're switching 2 partners, so this is double replacement. I could ask you what this is, but that's pretty straightforward. Notice that lead-4 is still lead-4. We're not losing or gaining electrons. This is not a redox reaction. And the last question. People sometimes are very confused on this, but it's really a question about conservation of mass. They said I have 90 grams of potassium chlorate. Some people would say, Mr. Grodsky, what's potassium chlorate? Well, chlorate from table E in your reference table is ClO-1. Potassium is a group 1 ion that's +1. Put them together, you get KClO. And there it is. So they're saying the reactant side, we have 90 grams. That's the mass of my reactants. And then they say in the problem, hey, if potassium chloride completely reacts, and I'm starting with 90 grams of it, and now when it finally reacts, I notice that there's 61 grams of potassium chloride. How many grams of oxygen should there be? People look at that like, I don't know. Well, wait a minute. The mass of the reactants have to equal the mass of the products. That's how all of this works. That's how stoichiometry works. That's how this mole ratio stuff works. So really the question is, 90 of the reactants has to equal 90 of the products because you're not destroying atoms and you're not creating atoms. That's why balancing works. Balancing is based upon that idea. I kind of drew this a couple times where I showed you that all the atoms on one side equal all the atoms of the other. Okay, so understanding this is just a concept of that. So noting that the total mass of the reactants is 90, and there's only 2 products, and the mass of one of the products is 61. The other one is, what number plus 61 is 90? Subtract, it's 29. 29 plus 61 is 90. The mass of the reactants is 90. The mass of the products must be also 90. If the other one is 61, subtract, and you've got the difference. It's just that simple. Okay? All right, so there it goes. I hope that helped. Good luck in your studying.